Imagine entering a home on a hot August afternoon where the outdoor temperature is 92 degrees, but the interior feels noticeably cooler despite no air conditioner running and no fans operating. The sensation isn't illusion or clever thermostat manipulation. It's the result of cross-ventilation harnessing natural air pressure differences to drive fresh, cool air through the home while exhausting warm interior air, all powered entirely by outdoor wind patterns and temperature differentials that cost absolutely nothing to access. Traditional homes across hot climates worldwide achieved remarkable summer comfort through cross-ventilation principles that contemporary American construction largely abandoned when mechanical air conditioning became dominant during the post-war era. The resulting loss of natural cooling capability has left most modern homes completely dependent on mechanical cooling even during moderate weather, when cross-ventilation alone could deliver adequate comfort at zero operating cost. Restoring attention to cross-ventilation in contemporary residential design and retrofit projects produces substantial cooling energy savings, improved indoor air quality, and enhanced occupant comfort that deserves far more mainstream attention than current efficiency discussions provide. Understanding how cross-ventilation works, what design elements maximize its effectiveness, and how existing homes can improve their natural cooling performance reveals one of the most cost-effective cooling strategies available to contemporary households. The fundamental physics of cross-ventilation exploits two distinct natural forces that drive air movement through buildings: wind pressure differentials between upwind and downwind building faces create pressure gradients that push air through openings on windward faces and pull air through openings on leeward faces. Even modest wind speeds of 5 to 10 miles per hour generate substantial pressure differentials capable of driving meaningful air exchange rates through properly sized and positioned openings. Thermal buoyancy effects create additional pressure differentials as warm interior air rises, while cooler outdoor air replaces it through lower openings. The combined wind and buoyancy effects can achieve air exchange rates of 10 to 30 air changes per hour in well-designed cross-ventilated spaces, substantially exceeding what mechanical ventilation typically provides while operating at zero energy cost. The traditional architectural precedents for effective cross-ventilation design extend across virtually every hot climate building tradition worldwide. Traditional Southern American homes featured dog-trot configurations with central open breezeways directing airflow through the structure. Mediterranean courtyards created pressure differential zones that enhanced ventilation through surrounding rooms. Middle Eastern homes incorporated wind towers called badgirs that captured prevailing winds and directed them into living spaces below. Traditional Japanese homes featured sliding panels that opened entire wall sections during summer, creating virtually open-air pavilions that maximized natural ventilation. The consistent architectural responses across independent cultures demonstrate that cross-ventilation represents fundamental building science rather than particular regional tradition, supporting its universal applicability in appropriate climates. Dr. Amelia Thornton Ashworth, a British-American building science researcher who has studied natural ventilation performance across diverse residential applications, has documented how proper cross-ventilation design can deliver 60 to 80% of cooling needs in many climate zones through passive means alone. Her research at major American universities examines comparative performance of diverse building configurations across summer conditions, quantifying the cooling contributions of specific design elements. The research findings provide evidence-based foundation for understanding which design approaches deliver greatest cooling benefits in specific climate contexts. The scientific foundation supports design decisions that might otherwise rely purely on architectural intuition and traditional precedents. The window placement principles for effective cross-ventilation require careful attention to building orientation, prevailing wind patterns, and interior space configurations. Windward side windows should be positioned to capture prevailing summer breezes, typically requiring attention to local wind pattern documentation from weather data. Leeward side windows should be positioned to exhaust warm air on the opposite building face, creating direct pressure-driven airflow pathways through the structure. Interior partitions should not block the flow paths between inlet and outlet windows. Window sizing affects airflow capacity, with larger openings producing greater air exchange rates. The combination of proper windward sizing, leeward exhaust capability, and clear interior flow paths creates effective cross-ventilation that couldn't be achieved through any single design element alone. Chidi Obiora Okafor, a Nigerian-American residential architect who has designed naturally ventilated homes across hot climate American regions, has documented how simple architectural adjustments can dramatically improve cross-ventilation performance in otherwise conventional home designs. His project experience demonstrates that attention to window placement, interior partition layouts, and outdoor vegetation creates substantial natural cooling capability without adding construction costs. The design integration with conventional home aesthetics demonstrates that cross-ventilation need not require distinctive architectural expression that deters mainstream adoption. The practical implementation experience expands cross-ventilation applicability to conventional residential markets. The stack effect contribution to natural ventilation provides additional cooling capability beyond pure cross-ventilation through horizontal air movement. Multi-story homes or single-story homes with high ceilings and raised roof vents create vertical air pressure differentials that enhance overall ventilation flow. Cupolas, clear story windows, and ridge vents, positioned at highest building elevations, exhaust warm air that rises through the structure. The combined stack and cross-ventilation effects can achieve substantially greater total cooling capability than either approach alone. The integrated approaches particularly benefit hot, humid climates, where every possible cooling contribution matters for maintaining comfortable conditions. The operable window requirements for effective cross-ventilation often conflict with contemporary architectural trends toward fixed picture windows and sealed building envelopes. Effective cross-ventilation requires substantial operable window area, not just small openings inadequate for meaningful airflow. Casement windows that open fully provide superior ventilation compared to double-hung windows limited to half-opening. Awning windows at viewer positions capture incoming breezes while blocking rain entry. The window type selection substantially affects ventilation effectiveness, independent of window thermal performance that contemporary efficiency codes emphasize. Now for the obstacles and limitations affecting cross-ventilation adoption in contemporary homes. First, the building envelope tightness priorities in contemporary efficiency codes conflict with cross-ventilation design requirements. Modern homes emphasize air-sealed construction that prevents uncontrolled air infiltration. While the tight envelope approach reduces heating and cooling loads during conditioned operation, it also eliminates the natural air exchange that cross-ventilation requires. The efficiency focus has largely displaced traditional ventilation design priorities in contemporary construction practice. Second, the outdoor noise pollution affecting many contemporary residential environments deters window opening that cross-ventilation requires. Traffic noise, commercial noise, and neighborhood noise make open window operation unpleasant or impossible in many suburban and urban contexts. The noise sensitivity particularly affects sleep hour ventilation that would otherwise provide substantial cooling during nighttime hours. The acoustic limitations affect cross-ventilation feasibility in ways that building design alone cannot fully address. Third, the outdoor air quality concerns affect ventilation acceptance in many contemporary regions. Urban and suburban air pollution makes outdoor air introduction problematic for households with respiratory sensitivities. Seasonal pollen concentrations affect sensitive occupants during spring and fall periods when natural ventilation would otherwise provide optimal performance. Industrial and traffic pollution in many regions affects ventilation desirability beyond pure comfort considerations. The air quality limitations affect cross-ventilation adoption in polluted regions where filtered mechanical ventilation seems preferable. Fourth, the security concerns affecting open window operation deter usage in many residential contexts. Ground floor windows particularly affect security concerns when opened for ventilation. Modern window screens provide insect barriers but not security against human intrusion. Window locks that allow partial opening provide compromise approaches but limit maximum ventilation capability. The security considerations substantially affect ventilation usage patterns beyond pure design capability. Fifth, the humidity introduction during ventilation affects comfort in humid climates. Opening windows during humid weather introduces outdoor moisture that can increase interior humidity beyond comfortable levels. The humidity sensitivity particularly affects hot, humid climates where cooling needs coincide with humidity control requirements. The dehumidification capability of mechanical air conditioning provides benefits that pure cross-ventilation cannot match in humid conditions, limiting cross-ventilation applicability in specific climate contexts. Despite these considerations, cross-ventilation deserves serious attention in contemporary residential design and retrofit projects for appropriate climate and site conditions. The economic analysis of cross-ventilation investment produces outstanding returns for appropriate applications. New construction implementations add minimal construction costs when addressed during initial design, but deliver substantial operational savings across building lifespans. Retrofit implementations adding operable windows or ventilation openings cost substantially more, but still deliver favorable economics in applicable contexts. Summer cooling cost reductions of 30 to 60% in moderate climates produce annual savings of $200 to $800 for typical homes. The operational savings compound across building lifespans to deliver lifetime benefits substantially exceeding any reasonable capital investment in ventilation design improvements. Mariam Diallo Ndiaye, a Senegalese-American sustainable design researcher, has documented how cross-ventilation optimization in moderate climates can reduce total cooling energy consumption by 40 to 70% through careful design attention. Her analysis shows that mechanical cooling becomes backup system for extreme weather rather than primary cooling approach, fundamentally transforming cooling energy economics. The research findings support design priorities that restore natural ventilation as primary cooling strategy in appropriate climates, relegating mechanical cooling to supplementary role during extreme conditions. The integration with mechanical cooling systems produces hybrid approaches, maximizing both comfort and efficiency. Smart thermostat systems can recognize when outdoor conditions support natural ventilation and deactivate mechanical cooling accordingly. Automated window systems can open windows during favorable outdoor conditions and close them during adverse conditions. Whole house fans provide mechanical assistance to natural ventilation during marginal wind conditions. The integrated approaches extract maximum benefit from natural ventilation when available, while providing mechanical backup when needed. The hybrid approaches represent practical contemporary evolution that maintains natural ventilation benefits within modern comfort expectations. The air quality benefits of cross-ventilation extend beyond pure cooling performance to include substantial indoor air quality improvements. The continuous air exchange flushes indoor pollutants, including volatile organic compounds from building materials, cooking emissions, cleaning product residues, and biological contaminants. The fresh air introduction provides oxygen-rich outdoor air, replacing depleted indoor air. The humidity management through air exchange prevents mold and mildew problems that affect sealed buildings with inadequate ventilation. The air quality improvements contribute to occupant health and comfort in ways that complement cooling benefits. Dr. Nkiruka Adelik Obasanjo, a Nigerian-American environmental health researcher, has documented how naturally ventilated homes produce substantially better indoor air quality than mechanically conditioned homes at equivalent outdoor air quality. Her research shows that air exchange rates in naturally ventilated homes often exceed mechanical ventilation system outputs by factors of 5 to 10, dramatically reducing indoor pollutant concentrations. The air quality findings support cross-ventilation promotion as health intervention beyond pure energy efficiency consideration. The public health framing expands cross-ventilation advocacy beyond efficiency-focused communities. The landscaping contributions to cross-ventilation performance can substantially enhance or degrade natural cooling capability. Strategic tree placement can funnel prevailing breezes toward home windows while shading windows from direct solar gain. Vegetation that blocks prevailing summer breezes reduces ventilation effectiveness, regardless of architectural design quality. Lawn areas create cooler microclimates than paved surfaces that radiate absorbed heat. The landscape integration with ventilation design represents often overlooked opportunity for performance optimization that requires coordination between architectural and landscape professionals. The night cooling strategies using cross-ventilation during cool, nighttime hours provide substantial cooling capability across subsequent daytime hours. The thermal mass of the home structure absorbs cool nighttime temperatures through ventilation operation, then releases coolness slowly through the following day. Windows closed during hot daytime hours retain the stored coolness while thermal mass gradually warms. The night cooling approach particularly suits climates with substantial diurnal temperature variations where overnight lows are substantially below daytime highs. The strategy represents traditional cooling approach used worldwide before mechanical air conditioning became dominant. Takashi Yamaguchi Sasaki, a Japanese-American sustainable design consultant who has specialized in traditional building science applications, has documented how night cooling combined with thermal mass can deliver full summer comfort in many American climate regions without any mechanical cooling. His project experience demonstrates that thoughtful integration of ventilation, thermal mass, and shading creates comfortable summer conditions at zero cooling energy cost. The comprehensive passive design approach represents contemporary evolution of traditional practices adapted to modern comfort expectations. The design validation expands passive cooling applicability beyond specialized green building contexts. The solar chimney enhancements to natural ventilation systems can substantially boost stack effect performance. Solar chimneys consist of vertical shafts with dark absorptive surfaces that heat rapidly in sunlight, creating strong updraft currents that enhance overall building ventilation. The solar-driven stack effect can move substantial air volumes, even during low wind conditions when passive cross-ventilation performance degrades. Integration of solar chimneys with traditional cross-ventilation creates robust natural cooling systems that function effectively across diverse weather conditions. The enhancement technologies expand natural cooling capability beyond what pure cross-ventilation alone provides. The climate-specific applications of cross-ventilation span substantial range. Hot, dry climates with low humidity and substantial diurnal temperature variations suit cross-ventilation particularly well. Temperate climates with moderate summer conditions support cross-ventilation as primary cooling strategy during most summer days. Hot, humid climates support cross-ventilation during non-peak conditions, but require dehumidification capability during extreme humidity periods. Cold climates benefit from cross-ventilation during shoulder seasons, but not during air conditioning season minimal in most cold regions. The climate adaptation determines optimal cross-ventilation emphasis across diverse American regional contexts. The research on historical building performance shows that traditional, naturally ventilated homes achieved reasonable comfort across climate zones that contemporary buildings would find intolerable without mechanical cooling. Southern plantation homes, Mediterranean-style coastal homes, and traditional southwestern adobes all delivered adequate comfort through natural ventilation combined with thermal mass, shading, and behavioral adaptations. The historical performance demonstrates that natural cooling can deliver comfort equivalent to contemporary expectations when properly designed, rather than representing compromised lifestyle, accepting reduced comfort. The historical validation expands natural cooling advocacy beyond specialized efficiency communities. Isadora Esteban Montalban, a Spanish-American architectural historian who has studied traditional cooling approaches across Mediterranean building traditions, has documented how sophisticated traditional buildings achieved comfort conditions that modern buildings often cannot match without substantial mechanical cooling energy. Her research shows that traditional buildings often performed better than contemporary replacement buildings at identical sites, despite the absence of modern efficiency technologies. The historical research validates attention to traditional design principles in contemporary applications, supporting revival of proven techniques alongside modern materials and construction methods. The Building Code integration for enhanced cross-ventilation requires modifications to contemporary construction standards that emphasize envelope tightness. Performance-based ventilation codes that allow natural ventilation credits reward passive cooling design. Operable window requirements beyond minimum emergency egress provisions support ventilation capability. Shading requirements for summer comfort reduce cooling loads that ventilation must offset. The code reform priorities supporting natural cooling integrate with existing efficiency frameworks rather than replacing them. The regulatory modernization can substantially expand natural cooling adoption in contemporary construction. The ceiling fan integration with cross-ventilation produces substantial comfort enhancements at minimal energy costs. Ceiling fans operating during ventilation periods accelerate perceived airflow across occupant skin, producing cooling sensation equivalent to 4 to 6 degrees of actual temperature reduction at fractional energy consumption compared to mechanical cooling. Large-diameter, slow-moving fans, often called high-volume, low-speed fans, move substantial air volumes across entire room areas at modest energy consumption. The fan integration maximizes comfort benefits from natural ventilation by ensuring effective air circulation reaches all occupant locations. The complementary operation between passive ventilation and mechanical air movement represents practical contemporary evolution of traditional cooling approaches. The whole-house fan systems provide mechanical enhancement of natural ventilation during marginal wind conditions when pure cross-ventilation performance degrades. Whole-house fans mounted in ceiling planes draw air from operable windows throughout the home and exhaust it through attic spaces, creating substantial air exchange rates on demand. Modern whole-house fans consume 200 to 600 watts compared to 3,000 to 5,000 watts for typical central air conditioning systems, delivering cooling effectiveness at roughly 1/10 the energy consumption. The whole-house fan technology represents mature intermediate option between pure passive ventilation and mechanical air conditioning, providing substantial cooling capability at modest energy costs. Bernadette Oakley Whitmore, a British-American building systems consultant who has designed whole-house fan installations across diverse American climate regions, has documented how these systems can meet most summer cooling needs in moderate climates while reducing cooling energy consumption by 70 to 90% compared to central air conditioning. Her project experience demonstrates that whole house fan operation during evening cooling periods combined with appropriate thermal mass can maintain comfortable conditions through following daytime hours without any mechanical cooling operation. The proven performance validates expanded adoption of whole house fan technology as mainstream alternative to central air conditioning in appropriate climate contexts. The window screen quality affects ventilation effectiveness substantially beyond basic insect barrier performance. Fine mesh screens restrict airflow more than standard screens, reducing effective ventilation capacity. Clean screens allow maximum airflow, while dusty or damaged screens reduce flow substantially. Removable screens that can be stored during cool weather allow maximum ventilation when insect protection isn't needed. The screen maintenance and selection affects ventilation performance in ways that simple architectural attention cannot fully address. Consider what cross-ventilation technology means for homes in appropriate climates seeking to reduce cooling energy consumption while improving comfort and indoor air quality. The thermal performance of 30 to 70% cooling energy reduction produces substantial operational savings. The indoor air quality improvements deliver health benefits beyond pure energy considerations. The minimal construction cost additions for new homes enable dramatic lifetime performance improvements. The retrofit applications in existing homes improve cooling performance at modest costs. The landscape integration opportunities enhance natural cooling through coordinated design. The thermal mass synergies extend cooling effectiveness across daily weather cycles. The stack effect and solar chimney enhancements expand performance capabilities. The hybrid integration with mechanical cooling provides comfort backup for extreme conditions. The historical precedents validate natural cooling effectiveness across diverse climate zones. The climate adaptation strategies optimize benefits for specific regional conditions. The code reform possibilities support broader adoption through regulatory modernization. The question isn't whether cross-ventilation deserves attention in contemporary residential design. The question is, why a technology that consistently delivers dramatic cooling energy reductions and comfort improvements has been largely abandoned in mainstream American construction, despite thousands of years of successful traditional applications worldwide. The answers involve construction industry priorities favoring mechanical systems over passive design, consumer expectations shaped by ubiquitous air conditioning, and efficiency code frameworks that reward tight envelopes over passive performance. For homes in appropriate climates and site conditions, cross-ventilation represents one of the most cost-effective cooling strategies available in contemporary residential markets. The traditional windscoop technology from Iran and Pakistan, called Badgirs, represents sophisticated natural ventilation approach that captured prevailing winds at tower heights above buildings and directed them downward into living spaces below. The Badgir technology predated mechanical cooling by centuries, yet delivered remarkable cooling performance in extreme desert conditions. Contemporary architects have adapted Badgir principles into modern residential applications, demonstrating that traditional ventilation technologies can inform contemporary sustainable design beyond their original cultural contexts. The cross-cultural technology transfer validates continued attention to diverse traditional approaches.